Oscar's not happy. Well, I'm not happy. Well, I am happy, but I'm not happy. So we left off saying how computers are unique in, and by the way, when I say computer, you know, you can think of smartphone and laptop and etc. So computers are unique in that they're multifunction devices. And they have a lot of capabilities, and that capability depends on the programs that are installed on that particular computer. So hopefully that makes sense, because programs are what let us, application programs, by the way, are defined as being pieces of software that let us perform certain functions. And so if we need to perform those functions, then we install that software. If you need to do your taxes, then... Are you driving, Patrick? No, I didn't think so. Because I didn't see, because you said you had a Tesla, and I know that they have that, you can drive, it'll drive for you. But I didn't see your steering wheel moving back and forth, so...
I'm at a customer site, and it's a medical device manufacturer. Everyone's on COVID alert.
Oh,
I have to wear it when I'm here.
No, but I was just wondering if your car was driving itself.
It can do that. We just got back from Utah. Most of the time it was driving itself, but my wife was at the wheel while I was doing this.
Yeah. Yeah, I didn't see the steering wheel moving back and forth, so I was like, oh, he must be parked somewhere. So... yeah, by the way, our cars are becoming more and more big computers that we can sit in. And, you know, it's just because Patrick has a Tesla. But even mine is, it has a hard drive, it has nav, it has all kinds of computerized sensors. It doesn't drive itself yet, but oh yeah, some cars have Wi-Fi, mine does not. Yeah, I wish I had a Ferrari. No, I have a bunch of cars, but my like go-to car is I have a BMW. So but don't think I'm all hoity-toity. I bought a used BMW. Tractors are large computers. Yeah. No, yeah, try to drive a tractor. But all cars, it doesn't matter what car it is. If it's new, my mother-in-law has a Toyota Honda Accord. Honda Accord. And she has, you know, it knows who's in the car when she's close to the car. It knows all kinds of things. It's really, really fancy schmancy. But computers are differentiated from one another by the software that they use. And so, and we control what software gets installed. Now, having said that, you know, how does that relate to us? Well, we're going to create application programs. We're going to create small programs. I'm not so sure that they're really application programs, but we're going to create programs that let the user do something. And so we kind of a little bit need to know how a computer works. And so what I want to talk about is the binary system and how computers process information, how they read information that's different to how we do. And so let me get my whiteboard up and I can, come on, there we go. So there are two methods in the world to represent data generally. And the one that the world we live in is what we call an analog world. And the world that computers live in is digital. And so in an analog world, there's a way to represent data. So if I want to represent the letter A in a regular world, I do that. Or I do, and I'll try to draw it nicely. There we go. That's a pretty good A. So if I want to represent the letter A, those in the Western, in our alphabet, I'm just going from where we grow up, where we are geographically. We have two ways to represent the letter A, capital and lowercase. And that's the analog form. Each shape represents a particular letter. Now, let me ask you just quickly, why? Why, and I'll just go with the capital A. Why is this a capital A?
Because we were told that that's the capital A, just learning.
Yeah. So we learned it was a capital A. We learned that that character represents an A. And why is it that shape?
Same reason.
Well, because at some point, right? At some point, somebody got together and said, let's use this for the A. And a bunch of other people said, awesome, let's do that. Let's use that as the A. And so we just arbitrarily agreed. It could have been that an A is that. It'd be much harder to write. Right, there's no reason that an A can't be this. Other than we've agreed that that is an A. So remember that even in the analog world, a lot of data representation is just arbitrary. There's no fixed, the only reason that we associate a sound with this A is because that's what we were taught. And so our brains automatically, if I say, what does this sound like? It could sound like A, it could sound like ah, right? We just associate that. And by the way, different languages obviously pronounce things differently. So they associate different sounds with letters, even if they use the same alphabet that we do. But the only reason that it's not intrinsic, I should say. It's not an intrinsic thing. So don't be confused just because that's what you were taught, that there's, it's better or it's worse than something else. It's just, it is what it is. So in the digital world, computers use electricity, and electricity has two states of being. Either it is on or it is off. So if I have a light like this, and I'm going to ignore the dimmers and stuff like that, because that gets too hard for a computer to work with. So we don't really use that with computers. So it's on now, right? The electricity is on. So if there was a way that I could electrocute myself here, I would be electrocuted. But if I flip the switch, the electrical state goes to off. So it's either on or off. Here, let me give you an epileptic fit. Right, so there are two states of electricity that we have to worry about, and they're on or off. So that is called a binary system because there are two ways to represent the electrical state. And we represent that with what we call bits, and a bit is either a 0 or a 1. Now remember that even the 0 or 1 is a representation of the electrical, there's no such word, electrical on-off state. Now, how many pieces of data can I represent by using a 0 or a 1 in a binary system? Is anybody there? 2 is correct. So I could say that the 0 represents red and the 1 represents blue. Are there more colors than that? Yes, there are. See, sometimes I do ask easy questions. All my questions are easy. Are there more than 2 letters? Are there more than 2 numbers? Are there more than 2 sounds? Are there more than, right? So when we have a binary system to represent data, it's not very useful because I cannot represent more than 2 things. So you can see that that is limiting by a lot. We can't really use bits to represent data. So what we have to do is we have to combine the 0s and 1s so that I have more options. And that's called a byte. So a byte would be at least 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Now, I'm not exactly sure what that represents, but so with 8 bits combined, now I can, does anybody know how many pieces, how many combinations there are there? If I have 8 spaces and in either space I can put a 0 or a 1, how many total, yeah, so it's 2 to the 8th, right? So it's an exponential value. It's 2 times 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 2. And Marco does have the correct answer. I can represent 256 different things. So an 8-bit byte gives me 256 different combinations. Now, are there more than 256 different colors? Yes, there are. Very likely. And there may not be more than 256 different colors, but there are certainly an almost infinite amount of different shades of color, right? So, I mean, how many different shades of blue are there? Well, it all depends, right? It's probably infinite. Now, does anybody know how many colors our eyes can see? Does anybody know the maximum resolution that our eyes can see? (1080p). Well, if you're sitting in front of a 1080p screen, I guess that's the best that we can do. We can see 10 million colors. 4K. 4K is actually about the highest resolution. I think it might be, and again, this depends on from person to person, right? So everybody's eyes are a little bit unique, but 4K is about the best that we can do. Why are they making 8K? I have no idea. Because it'll sell more televisions, because it must be better. I'll tell you why they're making 8K. Because when it comes to monitors, a television is a monitor. The bigger the screen size, the bigger the amount that the pixels become. And so if you get close to a very large television, it looks a little bit blurry. So going from 4K to 8K makes those pixels on the same size screen smaller, and we can get bigger televisions that still look really sharp. So basically, it's to make bigger televisions look as sharp as smaller televisions. I don't know if that makes sense. If you have a fixed screen size, and you have 1080p, that means that there are 1080 pixels left to right. And so on a very large screen, as the screen size expands, the pixels get bigger. That should make sense because there's a fixed amount of pixels. So if you have 4K, 4,000, or it's actually a little bit less, but we'll just go with 4,000 pixels, right? Then you can, on the same screen, the pixels are smaller. So then since the pixels are smaller, I can make it bigger before I start to notice. So the screen size can become bigger. And then with 8K, we have the same thing. Now, so we tend, that's my little monitor aside. Now, with colors, we agreed that there are more than 256 shades of color in the world. So we typically don't use 8-bit bytes to represent color. We add characters to, instead of using 8 bits, a lot of times we'll use 16 or 24 bit bytes. And I think with 24-bit bytes, I gotta look that up. 24-bit bytes, I think it's 14 million. What is it? $24 bits equals, I don't know why I can't remember. Usually I remember this off. It's 16.7 million. So about, and we lose some. So it's about 16.4 million colors. Yeah, Oscar, you're correct. The smaller your television, the less worry you should have about how many pixels there are, what the screen resolution is. That's why digital cameras and taking pictures with a digital camera, even if it's a smartphone, you probably won't notice the difference between a 5 megapixel and a 16 megapixel camera if you're printing 4x6s. Because at some points we can't tell the difference. And so if it's this small, you know, it's a 4x6 print, then it really doesn't matter when you get, you know, bigger than 5 megapixels. But again, a 5 megapixel image will start to look worse if you have an 8x10 or you blow it up on a computer screen or you start zooming in. So that's where the more pixels come in. So with 24-bit, we can do 16.7 million colors. And I'm going to just do here a search. How many colors can eyes see? Number of colors distinguishable by the human eye. Why doesn't it just give me an answer? So there's a huge article here and nowhere in it. $10 million. Yes, you were right. I was just double checking. So if we use 16-bit bytes for a camera, then that should cover everything that our analog eyes can see. So we're more than, you know, we don't really have to go over that. Now, there are reasons to go over that, technologically speaking, that will make things look a little bit better to us, but it's still, we're only seeing about 10 million. So, now, with data representation, a lot of times we're moving stuff around in 32-bit bytes or 64-bit bytes, hence the operating system. A computer can, a 64-bit operating system can move 64 bits simultaneously from one place to the next. So obviously that's going to be faster than a 32-bit system because you're moving double the amount of information at the same time. So let's talk about not just a binary representation of data with bits and bytes, but let's talk about a binary math. So you can actually do math in binary form, and there's a numbering system, and it's called base 2. So what is our numbering system? When I get too close to the edge, we are in base 10, right? So we have 10 characters. 0 through 9, by the way, not 1 through 10. 0 through 9. Now, in a base 2 system, there are only 2 characters. So we have, let's go with 8. 1, 2, 3, 4, 5, 6, 7, 8. And let me just put a number here. So here is a number. So now you have to actually speak to answer this. What number is that?
582.
582. And why is it 582? And don't say because I wrote it. You all know the answer. Why is it 582? Because the
way it's organized, we're taught that that sequence of numbers is 582.
yes, and so the 2 is what? Break it into pieces. The 2 represents what?
Ones.
Ones, yes. And the 8 represents?
Tens.
Tens and
Hundreds.
hundreds. And then the next, if there was one more, it'd be thousands and then 10,000s and 100,000s, right? We were taught that, and that's how base 10 works. So there are 2 ones and 8 tens and 5 100s. So it's 582. So when we just speak a number, we're doing multiplication, right? That makes sense, right? We're doing math. Because it's, 500. I have 500s, right? I've done a multiplication. 80, that's 8 tens. 2 is 2 ones. So where the number is placed is represents something different. I'm trying to undo here. And I can change this number very quickly so that we pronounce it differently. So if I just do this, now when you say the number, you would say it differently, right? We wouldn't say 500, well, we might say 582 minus 5,685, which would be a valid way of saying this, but this looks like what? What does it look like?
A phone number.
Yeah, it looks like a phone number. And you can be more enthusiastic when you say that. It looks like a phone number, so we would pronounce it 582-5685, right? What are we doing? We're removing the ones, the tens, the 100 spots because we know that this is not a mathematical number. This is a number that represents something else. It doesn't represent a quantity or a arithmetic value. Does that make sense? So for instance, let me do this. Let me click undo here a couple of times. just because I wrote it this way doesn't necessarily mean that this is 582. It could be 582, right? So there are two ways that we kind of represent numbers and that we read them. But in base 10 in arithmetic, each number has a ones, tens, hundreds spot. It's got a particular spot. So the same thing is true with base 2. And so in base 2, everything is, this is 2 to the 0th power. And this would be 2 to the 1st power. And this would be, and by the way, in base 10, it's 10 to the 1st, to the 0th power, 10 to the 1st power, and 10 to the 2nd power, right? So 10 to the 0th power is the ones. So if I have 3 tens to the 0, that's 3. If I have 5 10 to the 1st power, that's 10, right? So I have 5 tens, and then 10 times 10 is 100. So if I have 8, then it's 853. And by the way, this would be 10 to the 3rd. So that's 100 times 10. That's 1,000, etc. Does that make sense? So we're going to do the same thing, except we're in base 2. So that means I'm going to go 10 to the 2nd, 10 to the 3rd, 2 to the 3rd, I'm sorry, not 10, 4th, 5th, 6th, 7th. And that should be a 5. Does that make sense? So now I can represent a number. So let's do an easy number. So I'm going to fill the first bits up with zeros because it makes it too hard. And then we'll use this. So let's say, and it can either be a 0 or 1, right? So I have 1, 1, 0, 1. So what number is that? Well, I have 1 0 to the 2nd, so that's 1. I have 0 2s, so that's 0. I have 1 4. Well, that's not really true either. That is, yeah, that is 1 4. So I have 4. And then I have 3. 2 times 2 is 4 times 2 is 8. So I have 3 8s, which is 24. No, I have 1 8, I'm sorry, I have 1 8, which is 8. And so this number represents the number what number does it represent?
8,401.
No, because now you're converting it into base. Oh, does it? Yes, it does. 8,401. Yeah, you're right. I'm sorry, I'm losing my mind. So you can see that I've in base 2. That's what that is. And by the way, if I do this, let's do a different number here. Okay, so now I'm good. So if I do 1 1 0 0 0 1 1, and here let me get an eraser here because I want to erase this stuff. There we go. Okay, so what do we have? Well, let's start over here on the right. I have 0 2 to the 7th power. So I have 1 2 to the 6th power. That is 64. And then I have, oh no, we screwed that up. It's not 8,401. We need to add these together. I'm sorry. So I
Yeah, it
have
was
one.
supposed to be 15.
Yeah, I screwed it up. Yeah, supposedly it's 15.
Wait,
13. Sorry.
It's 13.
Because it
Yeah.
was 4, 8, and then 1. Yeah.
Yeah. So then here I have 32. And then 0, 0, 0. So there should be plus signs here. And by the way, there's a 0 here. And then plus, and that's 2 plus 1. And so I get 64. That's 96. 7, 8, 9. This is 99. So if I have a binary number and it looks like this, it is the number 99. Okay, yeah, I forgot to add. I'm sorry. I told you earlier, I woke up really late and I had to take a shower, and then I didn't get enough coffee this morning, and I didn't get enough cigarettes. And so, and from that point on, the rest of my day is going to seem rushed. So I'm screwed for the rest of the day. So my brain isn't functioning completely. I'm sorry. So, but anyway, this is 99. Okay, so we can see, and you can do math, by the way, in binary, and you just have to remember that the places are different. So what each character here, this isn't the ones and the tens and the hundreds, right? It's the ones, the twos, the fours, the eights, the 16th, how many 32nds, how many 64ths, how many 128ths, right? There are. So it means that we have to think, which this is why this is harder than base 10, because we were taught base 10 and we have been taught base 10 for years and years and years. Base 2 is binary. Yes. It's a binary system. Now, in this case, each 0 or 1 represents a numeric value. Instead of with a computer data representation where the bytes represent whatever it is that we need to represent, whether it's characters or like letters and numbers and emojis, or whether it's colors or sounds or the volume of something, etc. So a particular color. So this is just a binary system too. The reason that we talk about binary systems in computers is because we have, you know, computers are binary systems. So this is one good way to understand what how a binary system is different from a different system. So base 2 is different from base 10. And by the way, you can have base 3 or base 8 or base whatever. And all you do is it's still to the power 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It keeps going, right? And then you have zeros and ones for each spot. So you can have a base 8 system, and then this would still be 1, but this would now not be 2, it would be 8, because 8 to the first power is 8. So this would be 8, and then 8 times 8 is 64, and then 8 times 8 times 8, and 8 times 8 times 8 times 8, right? So the numbers become very big very quickly. Does that make sense kind of to everybody?
Yeah.
Okay, good. So, what time is it? We're done at 20, right? 11:20, yes. So, that's how binary system works. And that's basically how computers work as far as data representation goes. So, the next thing that we need to talk about is different bits of a computer. So I want to talk about what the different parts of a computer are, what is important. So let's start off with, and I know some of you are going to be good at this. So let's start off with a motherboard. What is a motherboard? And I just want to be very basic. I don't want to be very technical about this.
It's
So
what holds all
probably,
the other components.
I'm sorry?
It's what holds the other components.
Yeah, okay. And lets them do what?
Operate with each other.
You close. The word operate is a little bit, we have to be a little bit more specific. What is it? What does the motherboard provide? It does provide power, but more importantly, it's a place where we can plug stuff in, right? So all of our components are plugged into the motherboard. So what is the motherboard acting like? What does it let those components do? Why would we plug in everything to a motherboard? I keep looking to the right because your chat is up over here. So why would we want to plug them in? Why don't we just keep them separate? I'm trying to rephrase the question. What does the motherboard let us do? It lets us plug in the different components. And why would we plug them into a motherboard?
Well, because the motherboard acts like the I guess the skeleton, because the CPU would be the brain of the computer, and then the motherboard would be the skeleton of the computer.
It's the skeleton, which again, actually, you know what? It's not. I'm sorry, I just thought about that. It's not like the skeleton. If we were going to compare it, and Noah, you did get the correct answer, it lets the different pieces communicate with one another. It basically connects them to one another.
So would you say it would be like the nerves?
It would be, yeah, it'd be like the nervous system or the circulation system, right?
Yeah.
I guess the nervous system is probably better. But basically, it's a way for, I plug this into the motherboard here, and I plug this into the motherboard there. The motherboard provides a path where I can connect those two. Those two are now connected. So we plug things into the motherboard to let them communicate with one another. Otherwise, if I have a CPU sitting on my desk and a hard drive sitting on my desk and memory sitting on my desk, now power is another thing. A lot of those things need power. So, you know, the motherboard does provide power. Although not for everything, there's a power supply. But more importantly, even if they were all powered individually and it didn't provide power, the motherboard provides a way of communicating. So the motherboard is the main circuit board of a computer. The circuits are the wires that connect things in a traditional sense. And on a motherboard, they aren't wires, they're little metal paths that are printed onto the motherboard. Okay, next we have, and let's say the CPU. So what is the CPU? What does it stand for, first off? The central processing unit. And what does it do? It's like the brains of the computer. So it's like the brains of the computer. And basically it contains some circuits, logic circuits, that let it interpret and execute instructions. It lets it do math. So all of our math is done with a CPU. So arithmetic, not just simple math, but any math is done by the CPU. And when I say logic, it can do logical operations like, is this equal to this? Is this greater than or less than this? That's logic. Is this true or false? That's a logic operation. I don't know if you've ever seen a Venn diagram, but is this number part of this and this, right? Is this, so those are kind of logic operations. Hopefully that kind of makes sense. Then we have what we call RAM, which stands for Random Access Memory. Oh, by the way, the CPU plugs into the motherboard. Random access memory, they're memory chips, and they are the main memory of a computer. And basically any programs that are currently running, they reside, that's where they get put. They're running from RAM. And basically we use RAM because the CPU can very quickly access what's in RAM. So RAM is fast, very fast. It's quick to access and to transfer data from RAM to the CPU. So that's why when you start any program and it's on your screen, and even if it's minimized, it's running in RAM. Now, the one thing about RAM is that it's volatile memory, which means, and which is why we don't use it to store long-term information like files, is because when the power is turned off to the computer, the RAM can no longer hold a charge or can no longer remember stuff. So if you're working in Word, well, I always put it this way. When you start a computer, the first thing that happens is your computer, well, there's some other stuff that happens first, but the first real thing that happens is the computer starts the operating system, and we have to wait a few seconds. And basically what we're doing is we're waiting for the operating system to get loaded into RAM and start running. Once that happens, you get to your desktop. Then let's say we double click on the Word icon that's on our desktop to start that program. So we have to wait a second or two, depending on how fast your computer is, maybe even longer. But basically, again, what we're waiting for is for that program to load itself into RAM so that it can run. So once Word is up and you have a blank piece of paper, a representation of a blank piece of paper, you can start typing. Anything that you type is also stored in RAM. So if we're in Word and we don't have any kind of outside stuff to help us, and we're typing, and I am on page 24 of my 28-page research paper, and the power goes out, well, the computer turns off, right? What happened in RAM is because the RAM no longer got any power, is everything that was in it got dumped. So that means the work that you were doing, so the actual pages that you typed up, they're no longer in RAM, they're gone. The Word program is no longer in RAM, it's gone. The operating system is no longer in RAM, it's gone. So when we turn our computer back on, we have to go through the process again. The operating system has to load into RAM. We double click on Word, we load Word back into RAM. And all of the things that we had written are gone. We have to retype them. Now I know that Word has a autosave kind of a feature, which kind of tries to, well, it'll let you say, hey, there was some stuff that was there earlier. Do you want to recover it or something? But a long time ago, before that feature was implemented, hey, all of your stuff was gone. You had to start from scratch. Done. Tough patooties. So RAM is volatile, which is why we don't do any long-term storage there. So then and by the way, sometimes it's referred to as primary storage too. So we have secondary storage, which is long-term storage, which is basically flash drives and hard drives nowadays. No, I'm good. It's not easy to, even using this pen, it's not, I'm usually not this bad on a real whiteboard. So a hard drive or a flash drive is a way for us, or a thing that lets us store data long term, because it's memory that is not dependent on having power to it at all times. Now, if you want to access something from secondary storage, it does have to have power in order for it to work. So if I want to get a file off of my flash drive, it has to have power. And it has to be able to communicate with the CPU and the RAM. So it's got to somehow be connected to the motherboard. And so we have USB ports, right? We plug stuff in. And then the USB port is connected to the motherboard, which is connected to everything else. Hard drives, in this case, I have a solid state hard drive, 512 gigabytes. That's long-term storage. It's connected to the motherboard, and I can store stuff on it, but I can't save anything to it or read anything from it unless power is applied to it. But when the power goes away, anything that's saved on a flash drive or hard drive stays. Yeah, and RAM, you could consider the computer's short-term memory. And hard drives and flash drives can be long-term, you could think of as long-term memory. Then we have, it's time, but let me finish this little bit and then we'll just go off on our merry ways. So then we have input and output devices. Those also need to be connected to the motherboard somewhere, some way. And this is usually where I ask you questions, but in the interest of time, I'm just going to say them. So input devices. What are they? Well, a keyboard, right? Typically we have a keyboard. A mouse lets us input commands. Or a touch screen. By the way, a mouse is a pointing device. A touch screen is a pointing device, right? You can click on something. We all have phones that have touch screens. On your laptop, you probably have a what's it called? No, not a touch screen. What's it called? What's the thing? It's the pad. It's the, oh, good for you, Robert. I had a flip phone forever. What's the thing called that you touch with? Trackpad. A trackpad. Is that it? Is that right? Is Oscar right? My brain isn't working. Yeah, okay. Well, Oscar, you can't say yes, I'm right. Okay, so it's a trackpad, right? We touch it and we can move stuff around. Or touchpad. Touchpad sounds good too. So all of those things are, input devices. A keyboard and all of our kind of to enter commands and things. What other input devices do we have? A scanner would be an input device. A microphone would be an input device. A text scanner. I guess a camera is an input device, or a video camera. A camera can do video and graphics, so they're input devices. Microphone, yeah, that's pretty much it. Remember that we always can fall back on text, audio, video, and graphics. So there's always 4 things. So as far as output devices go, we have the monitor, some kind of display device. Because you don't have to use a computer monitor. You can use, like if I have a television, I wonder if I should hook that up over here. You can have an overhead projector, a lot of classrooms do. You can have a monitor. If you have a laptop, obviously the monitor is built in or part of the device. What other output devices do we have? Headphones, speakers, I'll just do speakers. Headphones are just very small speakers that we shove in our ears or over our ears. So speakers to output audio. Video is output on a monitor of some sort, a display device, and speakers. Oh, a printer. I forgot about printers. Printer is a standard output device. We can output graphics and text. Yeah, I think we're pretty good. I can't think of any more output devices or input devices, so that's it. Now, this is storage. These are storage devices. And down here. And these are volatile, so we don't use them for long-term storage. Okay, so having said that, are there any questions? Comments? Next Tuesday, we will talk about programming more, and I will probably assign during lab your first programming exercise that you should do. Okay? So I just want to give you a heads up. It's time to look at, make sure that you have looked at chapter 1 and start looking at chapter 2. Okay, so having said that, I'll see you guys later. Have a good day. And by the way, I will stick around for a few minutes if you have any questions or you have any comments that you want. It's not that scary.
I had a question, Professor.
Yes, I'm here.
So I was trying to do the practice on chapter 1 a little bit, like I was trying to do what you did yesterday with the input name, welcome to Python. And I don't know if I just downloaded the wrong version or what, but like it says to click like new window and run module, but those aren't on my.
Yeah, so here, let me show you. Let me minimize this and let me share my screen with you. Okay, so let me start. And like I talked about last time, right, I tend to just use the idle. Come on, go. I just tend to use this input. So the book is referencing a little bit older version of Python. So when it says new, what does it say, new module or new?
This is new window, I believe.
Or new window, yeah. Just do new file. You do have
Okay.
new file, right, Brandy?
Yes, I do.
Yeah. So what you will get when you click on that is this, which is exactly what you would get with the old command. They changed the word. And then when it says run module, basically it's just, it's in run. It should say run module is your first one. And by the way, if it doesn't say run module, you can always use the function key F5 to run it.
Okay. Yeah,
Okay?
before I had pushed the new file instead of new window because I'm like, I don't know if that's the same. I didn't have the run, but I do when I click the new.
Yeah, when you click new file, you get, see how I have two windows open? I have the shell, and then now I have the place where I can type a whole bunch of stuff. It's not just a command line interface.
Yeah, I just did it on mine to mirror you, and I have that.
And
I just
here
want-
is run module. Okay, so you're good then. Yeah, it's just that the terms are a little bit different.
Okay, that's
And
fine.
I think they did new file because everything uses new file. You know, if you in Word, when you click new, it says new file. So
Yeah.
I think they just did it to mirror all the other programs that we have, which does make it a little bit confusing, but yeah, it still works. So you should be fine. Okay?
That's fine. I was just worried. I was like, because I downloaded mine just ever so slightly different than you, and I was like, did I just download the wrong thing?
No,
And-
you're all right.
Awesome. Thank
You're
you
all
so
right.
much.
Yeah, no, that's an easy question. I love those. Okay, we'll see you later.